So I just want to start by thanking everybody for attending today and thanking the organizers for the opportunity to speak. I'm excited to be here, enjoyed the talk so far, and I'm looking forward to future talks. It's been a great digital event. So let me jump into it. Today I will be talking about adaptive experimental design methods for making many discoveries and some applications of these. So I'll start off with the standard adaptive experimental design loop. In many scientific applications, we are faced with a large set of potential candidates, and your goal is to discover some effective set of them. For example, in drug discovery, we may have access to thousands of compounds, and we are interested in finding the most potent ones for a specific target. The process generally looks like the following. First, we perform some set of experiments on these compounds, targeting a specific objective such as potency, and we collect some data. This data is then analyzed using various statistical and machine learning methods. And in many settings, we may use this data to then drive future experimentation and decide what to collect adaptively in a closed loop. So this is normally what's known as adaptive experimental design. So this process goes on for some time, and eventually we'll decide on a set of candidates that form our set of discoveries. At this point, the researcher can either choose to go and look at the set of discoveries and choose the best using prior or some other knowledge they have, or they may choose to start the process all over from the beginning on the smaller set. For example, they may decide to run some additional assays, or they may try to optimize for a different objective, such as the safety of the compounds. This talk is going to be focused on the question of how do we provide the researcher with an appropriately good set of discoveries in this adaptive experimental design loop that they can then go and perform additional expansive testing on. This problem shows up in many situations in large-scale experimentation, and it affects researchers in many domains. Examples from science include drug discovery, as I just talked about, or finding a set of small-length amino acid sequences that could fold into stable proteins, as another example. However, this large-scale experimentation also arises naturally in business domains. For example, large-scale A/B testing, where we need to decide among many different potential creatives, such as images, or text, or arrangement, to show on a website. In all of these settings, we are focused on two key goals. Declaring a set of good discoveries for potential further decision-making. So for example, in the drug discovery example, we may further be screening on objectives like safety or delivery mechanism. And in the A/B testing example, we may have further business rules that limit which creatives can get shown. But we're also interested in doing this in as few samples as possible. We don't want to waste samples or experimental budget on settings that we know aren't going to be particularly good. So far this has been a little bit abstract, and I want to ground some of these ideas in a concrete example. And so I want to focus on the specific example of the New Yorker Caption contest that I've had the opportunity to be involved with for the past few years. On the right is a picture of Bob Mankoff. He's the former cartoon editor of the New Yorker Caption contest. Each week, Bob selects a cartoon, generally with some humorous element in it. So for example, this cartoon over on the left of a boardroom with a plant as the chair, presumably. And he'll invite readers to send in humorous captions for this cartoon. He receives around 5,000 to 8,000 captions a week, and with the help of his assistant Colin, he would have to read through all of these captions to pick the funniest one. As you can imagine, most people they're not as funny as they think they are, and most of these captions are just not funny. And trust me, by the time you have looked at a few thousand of these, you probably have no real idea what funny is anymore. Hoping to do the judging in a more efficient way, Bob approached some colleagues of mine who were psychologists at the University of Wisconsin, and they kind of came to us asking, how can we try to find the funniest caption utilizing modern machine learning tools? Is there something smarter we can do than just looking at all 8,000 and trying to make a decision? And so the solution that we all finally settled upon was the idea of using crowdsourced voting. And it looks something like the following. Each week, we crowdsource the voting on captions to pretty much anybody who's interested in doing it. So you can actually see the URL here in the URL bar, newyorker.com/cartoons/vote. And when you visit the site, you're presented with a caption. So in this example, we see, "It's amazing to think he started out in the lobby." and you can vote on whether you think that's unfunny or funny. So I actually think that's pretty funny, like the plant was in the lobby, so I'm going to click funny. Okay, be patient. So once you vote, it gives you another caption to vote on, so be patient, he'll grow on you. Oh, yeah, I don't know. I don't actually think that's that funny, so I'm just going to click on funny. Okay, so this can go on for as long as you want, and you can vote on as many of these you want. So anyways, the goal is to determine the funniest caption using these crowdsourced votes. Every week, once this contest has been running for a few days, we present Bob with a set of funny captions, and from those, he exercises some editorial control and decides which one he wants to be the winner. Each week, we get over 1 million votes from users, and we've been running this crowdsourced voting contest for a long time. As a side note, we've had over 200 contests in it, and it's kind of turned into one of the largest human-labeled humor data sets. Bob has now moved on from The New Yorker, but we work with the current editor there, and it's been a lot of fun. And so this is a project that's been done it started while I was a grad student, and it's done in collaboration with Rob Novak, who was one of my former advisors at the University of Wisconsin, and Kevin Jameson, who's now a professor here in CSE. And so the key question is, how do we decide which captions we should show to voters to kind of get to this set that Bob can then select from? So before really jumping into it, I want to set up some models for how we can think about this problem and how we can think about the captions and the votes we're getting. So we consider the following model. For each caption I, we assume there's some unknown mean, or probability mu I, which represents that probability that a random person in the crowd would click on the ith caption. So we don't know this value, but we presume that it exists. So for instance, if mu is 1 for a caption, then that means everybody thinks the caption is funny. Likewise, if mu is 0, that means that nobody really thought the caption was funny. It didn't get any funny clicks whatsoever. And in general, a higher mu is better. In the following plot, on the x-axis, I have indexed the captions. And on the y-axis, I have plotted their means, which are unknown, between 0 and 1. So now, with this notation in mind, let's return to the question of what captions should we recommend? And for this question, there are generally 3 objectives that people commonly consider. The first objective is what's known as best arm, or best arm identification, where the whole goal is to return a single arm, which is the best one. So we focus our sampling, we focus on deciding what captions to show on discovering this best arm. A generalization of this is what's known as the top k objective. So for example, here in this picture, k would be 4. I'm interested in returning the 4 captions that have the 4 highest means. A final objective that's often considered is the fixed threshold objective, where I'm interested in returning all captions whose means lie above some fixed threshold. Again, I just want to emphasize, we don't know what any of these means are. We have to learn them through sampling. But our hope is to come up with methods that can return the answer had we known what these means are. So let's talk for a few minutes about what these different objectives are and what some of the pluses and minuses of them are. So first of all, in the case of best arm, one good answer isn't really enough. It's not really what Bob wants. What he wants is to be able to look at a set of potentially funny captions and then exercise some editorial control based on his experience as an expert in humor to decide which one to finally choose as the winning caption. For the top K objective, we run into various issues. And the main issue is well, how do you choose K? So for example, in the following plots, I've drawn a curve. This is kind of the drop-off of the means we saw before. And I'm going to assume that we just K to be like 100. So we're taking the top 100. In the example on the right, if I take that top 100, I end up with a set of means that, they're dropping off, but they're significantly higher than what's happening over on the left. On the left, the set of means I return from the top 100 contain a bunch of means that are not particularly good. The good ones are, there's very few that are high values. And so the problem you run into with the top K objective is that you have no guarantee on the quality of the captions that you end up returning. And you don't know, because you don't know what these curves are, you don't know how to pick K. Thresholds suffers from kind of a similar issue. How do you choose the threshold? Should I take it to be like 0.3? Should I take it to be 0.6? If I set it too high, I can even end up in a situation where I don't even return any captions or mark any captions as funny. So for example, if the threshold is this red dotted line, over in the left example, there's definitely examples above it, or captions above it, but over on the right, there aren't any, and so I wouldn't return anything. And so both thresholds and top K suffer from this problem that if you don't know the distribution of these means ahead of time, you don't have great guarantees on the set of items you may return. So motivated by this, me and some colleagues recently proposed the objective of epsilon good arm identification. It's very natural, but it hasn't really been considered in the adaptive experimental design literature, and it's something like the following. Find the set of arms, or captions, whose means are within a multiplicative factor of 1 minus epsilon of the best. i.e., if epsilon was 0.05, I'd want to return all arms whose means are greater than 95% of the best arm. A little more precisely mathematically, if my unknown means, so if I have n arms or n captions, and my unknown means are mu1, mu2, all the way down to mu n, I want to identify the set of arms I and n such that mu I is greater than or equal to 1 minus epsilon mu1. And I'm going to refer to these as the epsilon good arms. I just want to point out that, diagrammatically, it looks something like the following. Here's my best arm mu1, here's minus epsilon mu1 as my threshold, and I'm interested in all arms that are above this threshold. And I just want to point out that, unlike the previous fixed threshold case, where the threshold was specified ahead of time, the threshold in the epsilon good problem is dependent on the true unknown values of the means. And it's not some arbitrary number that's picked by the researcher. The threshold depends on the data in a non-trivial way, and it also has to be learned through some kind of sampling procedure. And so this is a key distinction. So how does this objective check out with some of the issues that we had before? Well, again, unlike best arm identification, it has the potential to return many good arms. It's trying to find all epsilon good arms. You have some guarantee on the quality of the resulting arms compared to top K. In top K, I don't know what the quality of those arms are going to be, but at least in epsilon good, I know that all the return arms I'm going to get are, for example, within 95% of they're all better than 95% of the highest mean. And finally, unlike the threshold method, I'm guaranteed to at least return one good arm, which would be the best arm. So I'm guaranteed to at least make some discoveries. I want to describe an algorithm that's going to be optimal for this problem of returning all epsilon good arms. But before I do so, and I'd like to do it without using as much math as possible, so before I do so, I'm going to have to introduce a few more concepts. After a certain number of votes on an arm, even though I don't know its true mean, I can estimate its mean by just taking the proportion or average number of votes for funny. This empirical average is going to be denoted with a mu hat. So for example, in this picture, I've drawn mu hat 1. That would be the average number of votes that came out funny for the first arm, and mu hat 2, the average number of votes that came out funny for the second. In addition, I can also define a confidence interval around mu hat, denoted by these red lines, which is guaranteed to contain the true mean in high probability. The width of this confidence interval is proportional to 1 over the square root number of votes. And so this confidence interval is guaranteed to control the true value, so this one will contain mu1 and this one will contain mu2. And critically, as my number of votes increases, these confidence intervals will shrink. So as I get more and more votes on each one of these arms, I know that I can estimate my mean better and better, and so my uncertainty goes down. And so based on these ideas, we can use them to develop an algorithm. At each time, we will choose a caption uniformly at random and show it to our visitor. So this is kind of the most naive algorithm we can do. This guarantees that the confidence intervals on each caption are going to be roughly the same length. So now what we really care about is identifying the captions above the threshold, which we don't know. However, based on this confidence intervals, we can construct a region that contains the threshold by taking the confidence interval around the highest potential mean and scaling it by 1 minus epsilon. This leads to this blue region, which is guaranteed to contain the true value of the threshold, 1 minus epsilon mu1. This allows us to conclude that any arm whose lower confidence bound is above this blue region must be epsilon good. And similarly, any arm whose confidence bound is below this blue region cannot be epsilon good. And so it gives us a statistical tool for deciding whether things are epsilon good or not. And so under our uniform sampling scheme, we keep sampling, and eventually the confidence intervals on all these arms will shrink, but at the same time, the width of the blue region will shrink as well. And so we'll get to the point whether we know if each arm is above or below the blue region, and we will know which arms are the epsilon good arms. However, this procedure could be very wasteful. Arms that are much greater or much lower than the threshold have been oversampled, and we really didn't need to know them to this level of precision. This is one of the downsides of non-adaptive experimental designs. They have the potential to waste samples by not being data-driven. Can we sample adaptively to do better? So based on this question, we developed an algorithm called ST-squared. Sample the threshold, split the threshold. ST-squared works something like the following. As before, we maintain a confidence interval, which is this blue region, that should contain the unknown 1 minus epsilon mu1. However, in addition, we look at the highest empirical mean, which we're going to denote as mu hat star, and we estimate our threshold, 1 minus epsilon mu1, using 1 minus epsilon times the value of this highest empirical mean. As above, we have a set of arms whose lower bounds are above the blue region, like these ones right here, and we have a set of arms whose upper bounds are below the blue region, and so these arms up here are necessarily epsilon good, and these arms down here are necessarily not epsilon good. We basically proceed in rounds, and in each round we're going to pull 3 arms. First, we'll pull the highest upper confidence bound. Since the threshold is defined in terms of the best arm, this guarantees that we are making progress towards reducing our uncertainty on the value of the best arm and hence the threshold. Secondly, we're going to sample the most uncertain, potentially good arm. And let me explain this more precisely. We look at all arms whose means are above our empirical estimate of our threshold that we are uncertain about, and then we sample the one with the smallest lower confidence bound. It's the one we're most uncertain about among the ones that are good. Similarly, we sample the most uncertain, potentially bad arm, which is defined the same way. You look at the arms whose means are below this estimate of the threshold, and you sample the one with the highest upper confidence bound. Sampling these uncertain arms has the effect of causing good arms to float up as we become more certain about them, and bad arms to float down as we gain certainty in them. And so to summarize, our sampling scheme has 2 components. Sample the upper confidence bound optimistically to learn our threshold. In addition, sample arms that we are very uncertain about but have the potential to be good or bad, respectively. The algorithm is written here in detail. It was developed earlier this year, working with a set of collaborators at the University of Wisconsin. This includes Blake Mason, a graduate student there, Ardhinder Tripathi, a postdoc, and Rob Novak, my former advisor, and I have a link to the archive paper. We were able to establish a sample complexity result for this algorithm presented here, and it's in this theorem. It's a bit technical to read, but I want you to focus on the first component right here. So let me just explain what's going on. I have a sum over my n arms, and this is how many times I will have to pull the nth arm. Notice that's a max of 3 terms here, and I'm just going to look at the first term, which is 1 over the distance from the ith arm to the threshold squared. So if this distance is very small, this quantity is going to be very big. This captures this intuition that it is more difficult to resolve arms near the boundary. The second term is a bit more difficult to explain, but it captures the difficulty of estimating the threshold to a given precision. And finally, there's some other terms in the sample complexity that I'm not going to describe. Very quick remark, we are able to establish lower bounds that show that this algorithm is optimal, but there are some subtleties. Some arms can get overpulled, and we have a way of contending with this, which requires a very different strategy, but ST-squared is optimal in practice. So finally, I'm going to discuss an empirical evaluation. So we consider a single contest, contest 651, and a cancer drug discovery dataset, which consists of 189 inhibitors against the kinase ACVRL1, and we judged multiple methods using the metric of F1 score, which is a metric that balances off precision and recall on the set of all epsilon good arms. So how well were other methods doing compared to ST-squared? So we compared several different options. The blue line is ST-squared. The green line is the naive uniform procedure. The Yellow line is UCB, which is an algorithm for finding the best arm that's common in practice. And all these LUCB lines refer to a top K algorithm. We set K in both cases to be the true number of epsilon good arms that we knew. Finally, we also looked at APT, which is an algorithm for thresholds. And basically, as the number of pulls increase, we're plotting the F1 score over time for these various methods to see how well they're doing. And the thing I want to point out is SD squared does almost as well as an oracle on a top K algorithm that knew K ahead of time, which is pretty incredible. SD squared is able to adapt to not knowing the number of good epsilon good arms and find them. It really, really beats epsilon good, or it really, really beats uniform. And it's interesting that the best arm identification strategy is flatline. The reason for that is they're only going after the best, and once they find that, they're not trying to find any of the other ones. So these were pretty promising empirical results, and I just want to put this work in a little bit of context. I have studied other methods for returning many discoveries, and in the threshold case, this was a paper 2 years ago in Europe, which was a banded approach to multiple testing with false discovery control, which was focused on the setting of multiple hypothesis testing where you want FDR control. There's also a paper last year where we thought about the setting where we have structure on our arms, and this was a paper in New Perspective Pool-Based Action Classification and False Discovery Control. And in future directions, I'm interested in combining the results from the all-epsilon problem with FDR control in multiple hypothesis testing, and also incorporating time-varying signals, which often arises in A/B testing settings. And so finally, I just want to say that up to this point, we've been using a best arm identification solution for the New Yorker, and we're excited to migrate that to ST squared, especially based off of the results of these experiments. So with that, I'm going to end. Thank you very much, and I am looking forward to your questions at the end.